All right, Algebra 2, 2.6, special functions. Specifically looking at piecewise functions today. So buckle up. This one's, in years past, this has been confusing for students. I'm going to try to make this very clear for you guys today. But do pay attention. You'll be able to review this video, I guess, whenever you want, if that's helpful. So, a piecewise defined function. It is simply a function that is written using two or more expressions. It has open and closed circles that are used on the graph to indicate whether a point is included or not. So basically, we are graphing two or more expressions on the same graph. Okay, so you can imagine what that might look like. This is a piecewise function, so the graphs are all in pieces. Okay, and we define where we want to put those by defining our domains. So you'll see really quickly what this will look like here with example 1. So for example 1, it says graph the function f of x equals, and then notice. Okay guys, let me just make sure this is clear to everyone. You're going to graph two different things. We're going to graph x plus 2 when the x values are less than 0. And then we're going to graph x if the x values are greater than or equal to 0. Okay, so what I like to do with these, you guys, I really quickly like to draw in my boundaries of where I'm going to have different graphs. So here, the boundary really is 0, right? When x is less than 0, something happens, and if it's greater than 0, something different happens. So I'm just going to kind of just drop down this dotted line here at x equals 0. Okay, and I know that when I am less than that line, I'm graphing the line y equals x plus 2. So I'm going to make that happen. I'm only going to draw this line. I'm going to graph this graph on this side of the picture. Okay, I'm going to end the graph early. Then, when x is greater than or equal to 0, so on this side of things, I'm going to graph the line y is equal to x. They defined it as f of x is equal to, I'm just changing that f of x to y. Okay, so most people know at this point how to graph the line y equals x plus 2. Okay, if you need to refresh that, you can refresh that. But what we're going to do is I'm going to just teach you a good strategy. Because you might have things that are like, that are not necessarily linear when we do these piecewise functions later on. So what I would do is this. What I would do is I would just make a t-chart. Okay, so if I'm making a t-chart for my first one, notice with a t-chart, you guys, you get to choose the x values that you put in, right? So here, this tells us kind of what x values to put in. We're going to use x values that are less than 0. Okay, so what happens if we plug a -1 in, or a -2, or a -3? So I'm going to plug those things in. Okay, so if I plug a -1 in there, -1 plus 2 gives me 1. If I plug a -2 in, I get 0. If I plug a -3 in, I get -1. So I'm just going to plot those points. Okay, so at -1, I'm at 1. At -2, I'm at 0. And at -3, I'm at -1. So I got this line happening, but it only goes up to 0. And notice here, you guys, that this is saying x is less than 0, does not include 0. So we're going to go right up to when x is 0, but we're not going to include it. So we might as well see what happens at this place. Okay, that's kind of an important idea. So even though this is saying x is less than 0, I'm gonna plug a 0 in and see what would have happened if I was at 0. So 0 plus 2 gives me 2. Okay, so at 0, 2, since I am not including this value, I'm gonna put an open circle here at 0, 2. Okay, and then I'm gonna connect through these dots. Okay, so I just graphed the line y equals x plus 2, but I stopped it short and I put a hole in the graph at x is equal to 0 because they only want me to graph this line when the x values are less than 0. That's what that means. That's all it means. Remember that these are your x values, these are your y's. Okay, so let's finish this. It says when x is greater than or equal to. Okay, so now we really do want to plug it a 0 in and put a solid dot there on this one. So I'm going to do a whole nother t-chart for my second expression. I'm going to start it at 0 actually. So if I plug a 0 in to y equals x, right, this is just y equals x, it's the second thing here. If I plug a 0 in, I get a 0 out, right? If I plug a 1 in, I get a 1 out. Plug a 2 in, get a 2 out. Plug a 3 in, get a 3 out. It's just the identity function, right? So at 0, 0, we have a solid dot. Then at 1, 1, we have a dot. 2, 2, we have a point. 3, 3, we have a point. And there's my line. Okay, that is a simple piecewise function. Hopefully that strategy makes sense. We'll do a couple more of them together here. But for example 2, I think we're going to go in the reverse. Yes. So for example 2, notice they give me a picture, and what they're wanting us to do is to actually come up with the piecewise function. So we're going to come up with, let me just erase this here quick. We're going to come up with this thing. Okay, they want us to come up with the equation, the piecewise function. So let's go ahead and do that. Here we go. One of the main things that we have to do is we have to remember to define the domain. Okay, so one of the first things that I like to do here is I like to just say, okay, f of x is equal to, and I never like drawing these things, but there we go, is equal to, now we have 3 different things happening here. Okay, so the first equation, we'll do the first equation if x is less than or equal to -3. How did I get that? Okay, here's how I got that. I want to graph this line when the x value is here at -3 or less. Right? That's what all these x values are. It's -3 or less. Okay, so I'm defining that domain. Then the second one I will do if x is between -3 and +1, not inclusive. Okay, so if x is between -3, oh, not inclusive though, sorry. Between -3 and 1. Okay, so that's that second one. The third one that I want to do, I guess I should do this in different colors, huh? The third one that I want to do will happen if x is greater than or equal to 1. See how this one starts at 1 and goes up from there in the x values? So that's the first step if you're looking at a picture and trying to come up with one of these piecewise functions. Now, what we have to do is we have to come up with an equation for each one of these lines, which is a little bit time consuming, but let's do it. Okay, the big idea here, guys, is if we go back to a couple lessons ago, if we know a point, or if we know 2 points for that matter on a line, we can find its slope and we can kind of find its equation. They're looking for the equation here. Okay, so let's look at some points. First of all, we have this point right here, which appears to be the point -3, -1. Okay, I need 2 points on a line in order to figure out the slope at least. So let me look for another point here. So it's hard to tell here, but I believe another point would be, it appears that there's another point, we're just going to assume that there is one there, at negative, what is that? That's -6, 0. Okay, so to come up with the equation for that line, you guys, we're going to find the slope. We're going to do the change in y over the change in x. So 0 minus negative 1 is just 1. Negative 6 minus negative 3 is negative 6 plus 3, which is negative 3. So the slope of that line, which this makes sense, as you look at this line from left to right, it is going down, right? So the slope is negative 1/3. Then let's just put a point in. Okay, so let's plug a point in. Now we could use our point slope form here, which I would encourage. So let's do that. So if we were to do that, it would be y minus y1. So I guess we can just use this point here. So we had to have y minus 0 is equal to negative 1/3 x minus negative 6, which is x plus 6. And then we'll simplify this, right? So y then is equal to negative 1/3 x. Negative 1/3 times 6 would give me negative 2. Okay, so the equation for that line is negative 1/3 x minus 2. And oftentimes I like to pretend this line kept going, Does it look like it would have crossed at negative 2? Yes, it does. So I feel good about it, and I'm done. So there's that one part of it. Now I got to figure out, well, this one's easy. What's the equation for this guy? Let me get my pen working here. The equation for this second guy is just going to be a y equals, right? So y is always going to equal in that little section of the graph 2. So it's just going to be 2. So we're just going to graph 2. Okay. Then for the third one, okay, looking at this piece up here, we're going to go back to the same strategy that we did before. I'm going to erase this a little bit here. We're going to get 2 points and we're going to figure it out. Okay, so let's look at this. One of the points appears to be 1, 3. That's this point right here. And then another point appears to be... it is hard to tell in this blurry picture. Does it cross right there? I'm uncertain. Maybe we'll use this one. So I believe it's going to go right there. Hopefully in your textbooks it'll be a little bit easier to see. And if there's, I'll give you as long as you're showing your work, you'll be okay. Let's just choose this one and see what we get here. So this one would be 3, 10, I believe. Okay, so if I wanted to find the slope for this one, it would be 10 minus 3 over 3 minus 1, which is 7 over 2. Okay, so there's my slope. And then I'm going to choose a point, right? So let's do this again. So for our point slope form, we have y minus y1, which would be, if we use this guy, we could be using 3, is equal to 7/2 x minus x1, 1. Okay, so if I do some simplification here, I get y minus 3 is equal to 7/2 x minus 7/2. Add 3 to both sides. If you add 3 to both sides here, and you want it to look at that as a half, that's the same thing as 6/2. So I can add 6/2 to both sides, and I would have y is equal to 7/2 x. If I add 6/2 to negative 7/2, I'm left with what? Negative 1/2? Something like that, assuming that point is correct. So this would be 7/2 x minus 1/2. Okay, and then I look, kind of look at that steepness. Does it look like it could cross at negative 1/2? I made it look like it's going to cross at a half. Here, hold on. Let's just see if this appears to, could it possibly cross right there? And I think it could, depending on how you look at it. But yes, this all does depend on choosing 2 points that appear to be solid on the graph. Okay, so hopefully your textbook makes that nice and straightforward. This blurry picture is not as straightforward, but that's okay. That is how you come up with piecewise equations looking at a graph. Okay, so you might want to study that example a couple more times. Here's another one, 2b. Okay, so for this one, let's just define it again. So we have f of x, and then we have three possibilities, right? The first one would be if x is less than 1. X is less than 1. The second one happens between 1 and 3. So we would say if x is, and notice this one's inclusive here. So we could say, actually it looks like -1, huh? Man, this first one is a negative. Sorry, guys. Okay, so this is a -1. So this would be between -1, including that -1, and 3, not including the 3. And then the final one, it is inclusive, would be if x is greater than 3. And we include that one. Okay, so sometimes that's the hardest part, is just coming up with the domain. I think it's kind of easy, but for some people that's difficult. But it's just identifying the x values and where those things happen. Now let's do the same thing we did before. Okay, so for my first one here, looks like we have a point. We can use this, even though this is not a point on the graph, we can still use it because it would have been on the graph, you know, if that would have continued, so that's totally fine. So let's do that. That looks like that appears at -1, -3. So we have a point at -1, -3. Let's get another point here. Looks like -2, -6 is also a point. Okay, so we can use that again to make our equation for our line. So let's look at that. That would be change in y, -6 minus -3 over change in x, -2 minus -1. That turns into addition, so this becomes -3 over -2 plus 1 is -1, which is just 3. So this thing has a positive slope, which appears to be correct. It's going up from left to right. And then we can go into our point slope form. So let's just use our first point there. So we have y. It's usually minus y1, so we're just going to add 3, right? So y minus -3 is plus 3 is equal to 3 times x minus x1, which would just be plus 1. Okay, so when I simplify this, I get y plus 3 is equal to 3x plus 3. So y is then equal to, if I subtract 3 from both sides, 3x. Okay, so it looks like it would go right through the origin, and that appears to be correct. So this would be 3x. I'm not going to do the next two for you guys right here just for the sake of time, but I believe you could do it. Just choose 2 points, right, and follow the exact same procedure. All right, so these take a little bit of time. That's okay. A piecewise linear function contains a single expression, so we could have a piecewise function that's a single expression where we just have a hole in the graph. So what that would look like is it would look like this line, but then like there would be a hole somewhere in the graph, and then the line would continue for some reason. Like we couldn't have one of these x values for some reason. That's also considered a piecewise function. That's a linear function. Okay, it's broken up into 2 pieces. It's technically just one single expression, but we have a hole in the graph. So it'd be like something like this: y equals 2x plus 3, where x cannot equal 1. You know, if we have something like that, there'd be a hole in the graph. The step function consists of line segments that look like this. These are typically created from a greatest integer function. So the greatest integer function has this notation where we have double brackets around some kind of value. That means the greatest integer less than or equal to whatever that thing is inside. So that's kind of interesting for people. The examples are the best way to explain these. So if you have the number 2.6, right, the greatest integer, the greatest whole number that is in this number is 2. In the negatives, it's a little bit weird because the greatest integer that is in something like -2.6 is actually -3, right? Because we're in the opposite direction because we're in the negatives. So the negatives of these are just kind of weird, but if you think it through, you just pause in the negative and you think it through, you'll start to get it, but you're gonna have to play with it a little bit. Okay, so here's an example of where you would use the greatest integer function. A recycling company pays $5 for every full box of newspaper, but they don't give you any money for partial boxes. Okay, so if you have partial boxes, it just doesn't count. Right, so for every full box, we get $5, right? So if we had 0 boxes, we would have 0, right? So from 0 to 1, we would just have $0. Okay, the whole in these things just says we don't include that at that place on the graph. If you have 1 box, notice we would get $5. But if we have anything between 1 and 2, so like if we have any partial boxes, we still only get $5 until we get to 2. And at 2, we jump up to $10. And then for anything between 2 and 3, we don't get anything, right? But then if we get the third full box, we jump up to $15. So this is an example of a step function, where typically it's only when we're dealing with like whole numbers, like an example like this with the recycling. And that would just continue on and on and on, but I'm going to stop it right there for the sake of time. Okay, we got a couple more of these apps. We just have the absolute value function with a couple of examples, and then you guys are on your own. Sorry, this is going to be a little bit of a longer video. That's all right. So the absolute value function looks like a V. Okay. For the parent function, the function is only defined above 0. So, from 0 and above, I should say. If we had a negative out in front, that whole thing would flip. Okay, so we're looking for these V shapes, and we'll learn about some transformations with these. So here we go. It says graph this function and identify the domain and range. All right, so let's just do this real quick. We know it's going to be a V shape. Okay, so if you're not getting a V shape, you're doing something wrong. This is an absolute value function. So let's just go ahead and plug in for anything, you guys. You can, like, if you're graphing something, make a t-chart, right? So I'm going to go ahead and do that. If I let's just start at -2 here, and then we'll do -1, 0, 1, 2, and then we might do a few more. But let's take a look. So if I plug a -2 in there, -2 minus 2 gives me -4. The absolute value of -4 is 4. So at -2, I'm at 4. Okay, if I plug a -1 in, -1 minus 2 is -3. The absolute value of -3 is 3. So at -1, I'm at 3. All right, plug a 0 in there, and I get -2. Absolute value of -2 is 2. So at 0, I'm at 2. I think you can see the pattern here. At 1, 1 minus 2 is -1. Absolute value of -1 is 1. And if I plug a 2 in, I'm at 0. Okay, so I have this thing, which is not going to be... This is not a complete... Right now, you guys, this is just a line. So you know you're not done graphing that if that's all you have. You have to go until you get this V shape. Okay, so let's just keep going. So at 2, we get 0. What happens if I plug a... Let's just continue on over here. If I plug a 3 in, 3 minus 2 gives me 1. Absolute value of 1 is 1. So at 3, I'm at 1. There we go. So now I've made the turn, and I can kind of guess that the pattern is going to continue. So there is the graph of absolute value of x minus 2. Notice the parent function always starts in the middle. Since the -2 happened inside of the absolute value sign, it shifts the whole graph left and right. Okay, so if it's a subtraction here, what makes x minus 2 go to 0 is actually +2. So the whole graph shifts to the right 2 places. And we'll talk more about transformations later. But we did talk some about those in Algebra 1. Okay, for example, for B. Now we have a negative on the outside, right? So typically that's going to mean that the whole V shape goes upside down. But then we also are adding 1. So let's just see what happens. Let's plug in a couple of values again. Let's start with the same values that I did last time. -2, -1, 0, 1, 2. We might need more, but that's okay. If I plug a -2 in there, absolute value of -2 is 2. then it's negative because the negative's on the outside. So I have negative 2 plus 1, which is negative 1. So at negative 2, I'm at negative 1. If I plug a negative 1 in, absolute value of negative 1 is 1. But then I take the negative of that, it's negative 1. Negative 1 plus 1 is 0. So at negative 1, I am at 0. Okay, then if I plug a 0 in, I'm at 1. Okay, if I plug a 1 in there, the absolute value of 1 is 1. 1 that's negative. Negative 1 plus 1 is 0. So at 1, I'm at 0. And look, there's our V shape. Right, so now that I've got that, I can kind of guess where that's going to go next. And we're done. Okay, so that's how you would graph absolute value functions. So guys, today, again, what we did was we figured out how to graph a piecewise function, and we looked at graphs of piecewise functions to create piecewise equations, and then we learned a little bit about absolute value functions and step functions and greatest integer functions. All right, so now it's time to practice, and we'll do some of this together in class. We'll see you.